So in order to start the automatic optimization of the rotor in Turbo Design 1, we start by loading the baseline rotor case, and we showed how to set this up in the previous demo. And so we can first start by adding the optimization, and in the target case we can see the rotor baseline has been selected, and the optimization workflow is rapid single point, which is basically direct optimization based on MOGA approach. And we can then turn on some optimization windows and arrange them a little bit. And of course we start with the input parameters, and we can see that the stream-wise loading parameters have been selected by default, and these are the parameters in fact that will be varied during the optimization based on these upper and lower bounds. And we can also add some extra parameters. For example, in this case we can choose to add the span-wise RVT star at the shroud trailing edge. And this is because this has a significant influence on the tip leakage loss in the rotor. And we don't select the mean trailing edge because we want to leave the mean value fixed. And if we keep the mean value fixed, then we don't need to worry about the overall work coming out of the rotor even after the optimization. So even though the shroud trailing edge or hub and the shroud values will be varied during the optimization, but the mean will be constant, and so the overall pressure ratio from the rotor will not change because of that. So we have added that as well. And what we can do then is by default we can see that the upper and lower bounds are plus minus 10% of the baseline value. But TD1 also has a range optimizer script, which basically runs a machine learning based algorithm to determine the upper and lower bounds for each of these parameters. And the reason we want to do it is because we want to explore a large design space, but at the same time we also want to avoid infeasible solutions. But before running the script, the range optimizer also takes into consideration your constraints, and so we need to set the constraints first. So we can see the throat constraint has been selected by default, and this is plus minus 10%, but in this case we want to constrain the throat more tightly within plus minus 1% because the throat is very important for setting the choke flow of the compressor, and so we don't want to really change the choke flow too much. Apart from the throat, we can also select the diffusion ratio, because this actually decides the possibility of flow separation, and so we usually don't want to keep it more than 1.8. And once we have set up the constraints, we are ready to run the optimizer script. So the range optimizer script, and the way we do it is by clicking this option here, estimate input ranges. And just like that, in 10 minutes or so, our automatic ranges have been set up for the different input parameters. We had already set up the constraints, and so the last step is to set up the objectives. And we can see the profile loss has been selected by default, and we can replace the secondary flow with the leakage loss parameter instead, because these two are very important in case of axial compressor rotors, and of course we have chosen to minimize both of them. And with the setup ready, we are now ready to start the optimization, and we can do this by clicking run from here. So once the optimization run is complete, which takes only less than half an hour or so on a single core machine, we can see all the designs on this 2D scatter plot between the two objectives, profile and the leakage loss. And then we can choose to see only the feasible solutions which respect all of our specified constraints. Or we can also choose to see the Pareto solutions, which are sort of the optimum set of designs from which we can pick and analyze any case of interest. And so in this case, for example, if we pick something from the middle of the Pareto front, and as a trade-off between the profile and leakage losses, then we can choose to analyze that case in TD1 for comparison with baseline. So as we can see, TD1 has now generated the design for the optimum rotor, and we can maybe name it to rotor optima. And in the performance window, we can then do some comparison between the two designs, and we can see clearly for the optimized rotor, the profile and leakage loss are considerably lower compared to the baseline values. And at the same time, the diffusion ratio and the throat are also staying within acceptable limits, which we had set as constraints before the optimization. And now let's have a look how the optimizer was able to achieve this. So we can start by comparing the blade loadings. So if you look at the span-wise distribution, while we had a free vortex in distribution in the baseline, now we can see that the optimizer has tried to reduce the loading at the shroud at the expense of the hub. And this is because it has tried to reduce the leakage loss at the shroud. And since we had maintained the mean trailing edge as constant, so this hasn't changed during the optimization. So the overall work or the pressure rise coming out of the rotor is not impacted because of this change. And now if we look at the stream-wise loading, we can see that compared to the baseline, the optimizer has tried to make both the hub and shroud as foreloaded. So there is higher loading towards the leading edge, and this is how it has been able to achieve that reduction in the profile loss. It is very important for the efficiency of these axial compressor rotors. And finally, we can also do some comparisons on the post-processing plots. So if we first look at the 3D plots, so this is the comparison of the blade shape between the baseline rotor in blue and the optimized rotor that is gray, and we can clearly see there is substantial difference between the shapes of the two blades. And then we can also compare these plots. So plots of let's say Mach number between the two designs, and it's clearly visible that the solid lines, which is the optimized design, it's showing a more uniform variation at all the three different spans from hub to shroud in case of the optimized rotor compared to the baseline rotor. And so once we are satisfied with the optimized rotor design, we can then again export the new design using the export options as we saw earlier, and then that can be used to do CFD analysis and for comparison with the baseline design.